Okay, our next example is similar to the previous one in that we're going to look at a beam and determine its capacity. This time we don't have any loads to deal with. We're just looking at a W21 by 41 made out of grade A992 steel, and we're going to figure out what the design moment strength of this beam is. We're going to assume that the beam has continuous lateral support provided along its compression flange. So we're going to go about this problem in the same way. Before we can figure out what limit states that need to be investigated for this beam, we have to first investigate the width to thickness ratios for the flanges and the web to figure out where we need to be in the specification and what the controlling limit states are. So let's start once again by looking at the flanges. W21 by 48 has a lambda for the flange of 9.47. That's tabulated in part 1 of the manual. Lambda sub p for the flanges. We said for rolled flanges, it's going to be 0.38 times the square root of E over Fy. For 50 KSI steel, that's 9.15. And now I'm comparing lambda to lambda sub p, and I see that lambda is larger. So I have to calculate lambda sub r to figure out if this shape is non-compact or slender. So to figure out lambda sub r, I need to go back to the specification. I need to go back to chapter B. So let me get back to chapter B. Here we are. Here's table B4.1. I'm looking at the flanges of rolled I-shaped sections, and lambda sub r is 1.0 times the square root of E over Fy. So I have 1.0 times the square root of E over Fy, and for 50 KSI steel, this comes out to 24.08. So what I can tell from this is that lambda for the flange is between lambda sub p and lambda sub r, which means that the flanges are non-compact. So let's deal with the web next. Lambda for the web is tabulated H over TW 53.6. Lambda sub p for the web we can calculate as 3.76 times the square root of E over Fy. For 50 KSI steel, that's 90.62. So comparing these two values, I see that lambda is less than lambda sub p, therefore the web is compact. So if I were going to classify the shape as a whole, I would choose the most stringent requirement. I would say that this shape is non-compact because when I compare the flanges, which are non-compact, to the web, which is compact, non-compact is a more stringent restriction on the section. Okay, so to figure out what to do with this information, I know that I'm not going to be able to reach the plastic moment capacity because the flanges are going to be less stocky, so they're going to be more susceptible to local buckling, and we're going to have to reduce the strength to account for that local buckling. So if you remember our relationship for local buckling, here's my nominal moment capacity, here's slenderness. It's a three-part curve, similar to the three-part curves that we've seen a number of other times. The flanges are in this region of the curve. The web is in this region where the web is not going to fail before the plastic moment. However, the flanges are susceptible to failure before the plastic moment is reached. So I'm going to flip back to chapter F. Let me navigate back down to chapter F. There's E. and there's F. So once again, I'm going to use user note F1.1. I have flanges in this case that are non-compact, and I have a web that is compact. So that means I'm going to be using the provisions in section F3. And I need to check lateral torsional buckling and flange local buckling. So FLB stands for flange local buckling. The problem statement said that continuous lateral support is provided to the compression flange, so I know that even though this lists lateral torsional buckling, that I really don't have to check it. But I am going to have to be concerned with flange local buckling. So limit states. I'm going to list them both here. Lateral torsional buckling, flange local buckling, and then I'm going to cross off lateral torsional buckling because we have continuous lateral support. But we are going to be in section F3 of the specification. So let's go ahead and calculate the capacity for flange local buckling. Once again, I want to sketch the solution space for local buckling. Here's my nominal moment capacity. Here's the flange slenderness. I have a three-part curve. First piece is the plastic moment strength. The next piece is a reduction in capacity in the non-compact region. And the last piece corresponds with elastic local buckling. So this first piece is going to have a y-axis value of m sub p. The first anchor point is going to correspond with a slenderness value of lambda sub p. The next anchor point is going to correspond with lambda sub r and a moment strength of 0.7 my. So we are somewhere in this non-compact region because I calculated a lambda value that was equal to 9.47. So lambda sub p we calculated was 9.15. Lambda sub r we calculated was equal to 24.08. And then the lambda that we just calculated for our flange was 9.47. So there's our lambda. That means our capacity is going to be really pretty close to the plastic moment. But our job is to figure out what that nominal value for moment is. So I'm going to flip back to section F3 in the spec. Scroll down a few pages. Okay, here's F3. F3 applies for doubly symmetric I-shaped members with compact webs and non-compact or slender flanges in flexure about their major axis. So we have that. We don't need to worry about lateral torsional buckling because we have continuous lateral support. But we do have to worry about flange local buckling for the compression flange. Since we have non-compact flanges, we're going to be using equation F3-1. Now at first, equation F3-1 looks a little complicated, but after you get a sense for what it's doing, it's actually one of the more straightforward expressions in the manual. So I'm going to write that expression out. The nominal moment capacity for flange local buckling is the plastic moment strength minus the plastic moment capacity minus 0.7 Fy Sx times lambda minus lambda p for the flange divided by lambda r for the flange minus lambda p for the flange. And this is equation F3-1. So let's look at what's happening in this expression. I have the plastic moment minus the distance between the plastic moment and 0.7 my, because this is just 0.7 my. And then I'm just figuring out where I am in between lambda sub p and lambda sub r. So all this expression is doing is figuring out, using linear interpolation, where I am along this straight line portion in this non-compact region of the curve. So this is just a linear interpolation expression to figure out this value right here. So let's go ahead and calculate that. Plastic moment strength is going to be Fy times Z sub x. Fy is 50, Z sub x is tabulated. If I multiply them together, I get a plastic moment strength of 5,350 inch kips. And you do have to be careful with units when you use this expression, because when you plug in for S sub x, you're going to be plugging in a value in the units of inches to the third. So I suggest that you continue using inch kips in this expression, and then you can convert over to foot kips at the end if you want. So I have 5,350 inch kips minus 5,350 inch kips minus 0.7 times 50 ksi times an S sub x value of 93 inches cubed and then let me continue down here. Here's my interpolation between the lambdas. Lambda for the flange we found was 9.47. Lambda sub p was 9.15. Lambda r was 24.08. And lambda p is 9.15. Now when you use this equation, it is very easy to do the order of operations incorrectly. Make sure that you do multiply this quantity by this quantity before subtracting that whole expression from m sub p. So m sub n comes out to 5,305.1 inch kips, which if I divide by 12, I get 442 foot kips. Now I factor that to get my design strength, and I have a resistance factor of 0.9 times 5,305.1 inch kips, or 0.9 times 442 foot kips, which is equal to 397.9 foot kips. So my conclusion is the design strength of the beam is 398 foot kips, and it was governed by compression flange local buckling.